Hi everyone, welcome to AI Tech channel. This is Akash Kingwar and today we'll be studying different integrals lecture 1. So before moving further, let's discuss what kind of questions can be asked in this particular chapter. So basically, they won't be asking you questions they won't be asking you to calculate integration with the help of indefinite integration and then just putting the limits over here. They won't be asking such kind of questions in case of different integrals. So what they'll be asking you property based questions. So most of the questions we have got earlier in PGDBA regarding different integration, we have always got property based questions, but most likely they'll not be asking you questions based on indefinite and then you have to just put the limits with the help of different integration. So basically you have to focus more on the properties. So first of all, we have understood indefinite integrals as the reverse of differentiation. But now let's try to understand different integrals with the help of area. So let's suppose we have this one particular curve. This is point A, this is point B. And what I have to do, I have to calculate the area under this curve between this range A to B. Now this value is FA and this value is FB, right? Now what I'll do to calculate the area, what I'll do, I'll try to divide this entire area into thin strips, very thin strips. So let's say I have done this. So this is dx. Let's say this is length dx. This dx is as good as h, which we use in limits. That is infinitesimally small, right? Uh, but why this idea came to our mind to do this kind of summation to calculate the area? Basically, let's say if I divide this entire area into squares, into rectangles, sorry, not squares, what I can see, I can see this particular portion being left out when I'm calculating the area of this particular rectangle. So basically what I'm trying to do over here, I'm trying to approximate the area of this curve by drawing rectangles. But in this process, I'm missing out on this particular area which is being left out. So to reduce that area to a very small number or a very small fraction, what I'll do, I'll try to reduce the length to the width of this particular strip. So that's what we are doing actually over here. So I've taken this strip of length of width dx, which is at a distance of x. So this dx is infinitesimally small, just as good as h. And what about this height? This height would be f of x, right? Because this function is fx, and at x, this particular value would be fx, and that is equals to height. So area of this strip would be length multiplied by width, that is dx. Now I have to do summation from here to here to get this entire area, right? But now when I'm doing it at a very small level, at a very infinitesimal level, in that case I can replace this summation with integration, and that is what differentiation all about, calculating the area. So this range goes from A to B. So if we are doing this, then actually what we are doing, we are calculating the areas of thin strips and then adding them entirely to get the area of this particular curve, right? Now one problem over here is, let's say we have a curve of this sort. Now when we are calculating just the definite integral, in that case, this area above x-axis would be positive and this area below x-axis would be negative. And when we are calculating definite integrals, in that case, we have to add them algebraically. We don't have to, take the modulus and then add. We don't have to do that. We have to add them algebraically. In case of we are calculating just definite integral. Now, let's suppose we are calculating the area. In that case, what we'll be doing? We'll be making this as positive. Basically, we'll be taking the modulus over here and then we'll be adding, because area cannot be negative, right? Let's say this comes out to be plus 3 and this comes out to be minus 4. If we do just the integration, different integration, we'll be getting minus 1 as the answer. But minus 1 cannot be the area. So that is why what we'll be doing the modulus over here and adding then with 2 plus 3. That would give us 7, right? Now let us talk about basics of different integrals and changing of limits. So let's talk about first what we studied in indefinite. We studied that integral small fx dx would be capital Fx plus c. But in case of definite, small fx dx from a to b, that would be capital Fb minus capital F a. We won't go into the derivation because that is not a part of PGDBA syllabus and that would actually waste our time to do that. So we'll just remember this property, that integral fx dx would be capital Fb minus capital Fa. So whatever the integration you're getting over here, you have to apply limits in such a manner. let's say we have multiple functions over here, let's say fx plus gx. In that case, let me write it once again, fp. So let's say we have fx plus gx dx. In that case, what we'll be doing, fb plus capital GB minus fa plus capital GA. We'll be doing this, right? Now coming to the changing of limits, you will be doing, in case of indefinite integration, you will be doing a lot of substitutions and all these things. So basically your limits would change. Let's say, for example, we have integral 2 to 3 and ln sin x and cos x dx divided by sin x. Let's say we have this integral. So the obvious substitution over here would be take ln sin x equals to t, right? We'll get 1 by sin x multiplied by cos x dx equals to dt. So eventually our integral would become t dt, right? But what about the limits? Over here, what we did, we took this kind of substitution. So when this x is 2, t would be ln sin 2, sorry. And when this x is 3, t would be ln sin 3. So this is how we have to change the limits in order to do the integration. Or else what you can do, you can take the substitution, do the integration, revert back the substitution, basically put back the substitution, and then you can apply the regular limits. That is also one way. Either way you can do it. Now let's look at one basic example to demonstrate the same. So we have integral 3 to 8 sine of under root x plus 1 divided by under root x plus 1. So the obvious substitution over here we have the bracket. So the obvious substitution over here would be under root x plus 1 would be t. So basically 1 upon 2 root x plus 1 dx equals to dt. So basically dx divided by root x plus 1 equals to 2 times dt. So what we are getting over here, 3 to 8, 2 times sine t dt, right? And not these limits. So basically we have done this substitution. So when x equals to 3, t would be 2, right? Because 3 plus 1, 4 under root 2. And when x equals to 8, t would be 3. So this should be the final expression. So with the help of isolate, this function would be first function, this would be second function, right? So this integral would become first function into integral of second, first function into integral of second minus integral of derivative of 1, that would give us 1 upon 1 plus 2x dot 2 into integral of second, that would be x square by 2. 2 gets cancelled out, right? Now this would become ln 1 plus 2x dot square by 2 minus integral of x square by 1 upon 2x dx. Now this is a very standard format, right? We have to change the numerator over here. So let's take this one over here. So what I would do, I would divide by 4 and multiply by 4. That would give me 2x square. And what I'll do, I'll add and subtract minus 1, plus minus 1 basically, and plus 1. Divide by 1 plus 2x and divide by 1 plus 2x. So this becomes the standard one. This is the standard one. And over here, what we can do, 2x plus 1 and 2x minus 1 divided by 1 plus 2x. Integral 1 by 4. This gets cancelled out. Again, this becomes the standard one. So this was just to demonstrate that in this case, you haven't done any kind of change in the limits, but you have to do first the indefinite integration, and after that you have to put the limits. Like, although we have seen these two examples, but these kind of questions are highly unlikely to come in the actual examination. In actual examination, property-based questions are highly likely to appear. Now let's look at first property that says integral a to b fx dx equals to integral a to b ft dt. That is very obvious, right? Because we have just changed the variable. So in this case, we are variating t from a to b. Over here, we are variating x from a to b with the same function, right? So that is very obvious, but the proof is actually x equals to t. Take this substitution, so dx becomes dt. So you have to just put this over here and we'll get this expression. So that is the very simple proof. And now let's talk about property 2. It says integral a to b fx dx equals to minus of b to a fx dx. Again, that is very simple. So basically integral fx dx is, let's say, capital Fx, right? So basically this would be fb minus fa, and this would be minus of fa minus fb. This eventually becomes fb minus fa only, right? So these two are same. So what does this mean? If we have to change into negative sign, then we have to reverse the limits, or vice versa. Now let us look at third property. It says integral a to b fx equals to a to c fx dx plus a to b fx dx. Basically, we are breaking down the integral at a point c where there's a point of discontinuity or the definition of function changes. For example, let's say we have fx equals to mod x. So basically, this definition is changing at x equals to 0. In such a case, let's say we are integrating mod x from -1 to 1. In that case, we know that the definition of function is changing from x minus x to x at x equals to 0. So what we'll be doing, -1 to 0 x dx plus 0 to 1, sorry, minus over here, minus x dx, x dx, right? So we'll be breaking down our integral according to this. Similarly, for the case of discontinuity, let's say we have fx equals to tan x, and we are integrating from 0 to pi tan x. So basically, we know that we have a discontinuous point at x equals to pi by 2. So what we'll be doing, we'll be integrating from 0 to pi by 2 tan x dx plus integrate from pi by 2 to pi tan x dx. So this is how we have to do. Now the interesting point over here is people actually tend to identify the points where definition of function is changing, but they tend to miss out on the points where the function is actually discontinuous, and then what they'll do, they'll just integrate it directly. So that is the kind of traps you can expect in the actual questions or actual examination. So this is the point of trap you can expect in the actual examination if the question is going to be difficult. Otherwise, it's going to be simple. Let us look at this example. It says integral 0 to 3 GIF function of x dx. Now we know that GIF function is a piecewise function. It's separately defined from 0 to 1, 1 to 2, 2 to 3, and also it's discontinuous at integral points. So basically this function looks like from 0 to 1, this is actually 0. From close 1 to open 2, this is actually 1. And from close 2 to 3, open 3, it's actually 2. So basically this is 0, this is 1, and this is 2. So we have got the definition from here. So from 0 to 1, we'll be integrating 0 dx. From 1 to 2, we'll be integrating 1 dx. Plus from 2 to 3, we'll be integrating 2 dx. Now this is a very simple example. You must be thinking that this is a very simple example. The trickier version can be, let's say they are asking x raised to power 2, 0 to 3. Now in that case, you'll have to take the roots into consideration, because from 0 to 1, it's fine. But from 1 to root 2, we'll have to take the step over here. You'll have to divide the integral over there. And then from root 2 to root 3, then you have to do that, right? So you have to do it in this manner in case of this kind of function. Similarly, this also can create such kind of problems. So if you want to practice a difficult version of this question, then maybe you can do root x or x square or x cube, whatever. But that is the maximum kind of difficulty you can get in step function. Now let us look at this example. We have 0 to pi under root 1 plus cos 2x divided by 2 dx. Now I have told this earlier many times that whenever you see 1 plus cos 2x, the first thought should be 2 cos square x, regardless of if you are going to use it or not in the question. But your first thought, first trigger thought should be 1 plus cos 2x equals to 2 cos square x. And similarly for 1 minus cos 2x, it should be 2 sin square x. Now 0 to pi, this 2 gets cancelled out, this becomes cos square x dx. Now here's the interesting part. In case of indefinite integration, what we used to do, we assume that the entire function is in the domain. So basically domain is not breaching, and we used to take this out as it is. So basically it became cos x just like that. But in case of definite integration, since we have been defined a range, so this becomes a definition changing function. So 0 to pi, this becomes mod of cos x dx. So that is the point where many people actually do mistakes. Now this would become 0 to pi by 2. We know that cos is positive in first quadrant and negative in second quadrant. So this would become cos x dx minus from pi by 2 to pi cos x dx. This minus became because definition is changing over here at x equals to pi by 2. Right? So this is the actual answer for this integration. Now let us look at one more example. This says minus pi by 2 to pi by 2 integral under root. I'll take cos x as common, 1 minus cos square x dx. Now what is this? This is minus pi by 2 to pi by 2 integral cos x dot under root of sine square x. And just we did this same thing in the previous example, that whenever we are doing definite integration, we'll have to take the mod x, mod sin x over here. So that would give me mod sin x dx. Now we know that cos x is positive from minus pi by 2 to pi by 2, so that is not going to change anything. But in case of sin x, we have negative values from minus pi by 2 to 0 and positive values from 0 to pi by 2. In that case, we'll have to change the definition of function at x equals to 0. So this would give me minus pi by 2 to pi by 2 under root cos x dot minus over here sin x dx plus integral, not pi by 2 over here, this is 0, plus 0 to pi by 2 under root cos x dot sin x dx. So this is how you have to break the function. And then it's a very standard integral. Basically, you'll have to take cos x equals to t. That would give you sin x dx as dt. That's a very simple example. So today's lecture was till here only, and we studied 3 basic properties of definite integration, and the remaining 4 properties will be studying in lecture 2 and lecture 3. So let's meet tomorrow. Thanks for watching.